So can you briefly explain where the limits come from?
You mean how these regions were drawn?
Yeah, the empirical.
Okay, so some come from diffraction experiments. So people try to do diffraction experiments, like double slit experiments, basically, or some variant of that, with larger and larger objects, heavier objects, with big molecules. Say. Um, Thousands of times the mass of a hydrogen atom. Okay, so that puts some constraints, and also there's also a question of time of flight that plays a role. So many of these experiments are not specifically done for testing GRW theory. They're done because people want to have more and more extreme diffraction experiments over larger distances with heavier objects. People often talk about testing the limits of quantum mechanics. How can you do diffraction experiments and still see interference patterns with heavier and heavier objects? Okay, so
yeah,
that puts some of the constraints here. So some part of the empirically refuted region comes from these experiments.
How old are these limits?
Okay, so the diagram that I'm showing you, that was from 2011. So actually, in the meantime, the boundary of the empirically refuted region has already moved. So in these diagrams, you see 2 points in the plane that are marked. One point is labeled GRW, so that's the value that the values that GRW proposed for sigma and lambda. Another point, different values were proposed by Adler, and in fact, Adler's values have by now been excluded, at least for GRW, not for the CSL version. I'm not sure about the CSL. I would have to check that. So for GRW, the Adler values have by now been refuted by gravitational wave detectors, by the LIGO experiment. So the LIGO experiment, by the way, also has consequences for the possibility of collapse theories such as GRW. For the most up-to-date versions of such diagrams, you should search for papers by Angelo Bassi. Bassi is kind of is one of the leading people for empirical tests of collapse theories. So in his papers, he has diagrams like these that also include more recent experiments. Okay, welcome back, everybody. Now, Albert, if you want to ask another question, please go ahead, or else I will move
no,
on.
you can continue.
Okay, then I'll move on to the issue of ontology. Now, ontology, the word ontology already sounds kind of strange, sounds very philosophical, but ontology is also a technical term. For example, in computer science, it's a technical term, so they have theorems about possible ontologies. It's also a technical term in the foundations of quantum mechanics. Here's what it means there. The ontology of theory T is what exists in the world according to T, which is actually also kind of the philosophical meaning of them. But okay, so in philosophical writings are sometimes very unclear. So here it's a kind of a physical thing. Okay, so for example, the ontology of Newtonian mechanics consists of space, a Euclidean three-dimensional space, time, the time axis, and particles, Q. The ontology of Bohmian mechanics consists of Euclidean space, three-dimensional space, time, particles, and a wave function, psi. So these are the things that Bohmian mechanics says are really there. It was long thought that the key to clarity in quantum mechanics was to avoid talking about ontology and to stick to operational statements, which means statements of the kind, if you do this and this experiment, then the outcome will be such and such. But frankly, that thought has not paid off. On the contrary, those theories that had a clear ontology, clear statements about what is actually there, they have advanced the field more than the discussions about operational statements. Basically, that's because there's agreement about what will be the outcome of certain experiments if you set them up in a particular way. A similar word to ontology is the word beables. So this is a word coined by John Bell, beables in contrast to observables. This word means the following. Beables are the variables in a theory that represent the ontology, the things that exist. The beables are the quantities that actually have values, in contrast to observables, which don't actually have values. The word beables is also meant to suggest a kind of tentative character, like it could be, because what the beables are depends on the theory. So different theories or different proposals for how the world might work, and they could have different beables. They could posit different possibilities for the for the ontology. For example, Bohmian mechanics makes the hypothesis that particles are literally material points moving around. They have trajectories. GRW theory denies that. In GRW theory, there are no trajectories. Now, another concept that I need to talk about is the primitive ontology. So what does that mean? Primitive ontology is the part of the ontology that represents matter in three-dimensional space or four-dimensional space-time. For example, in Bohmian mechanics, the ontology consists of the particles and the wave function, and of course space itself. Okay, let's focus on the particles and the wave function. The primitive ontology consists of the particles, that is the stuff that's really in our space, in three-dimensional space, whereas the wave function is the stuff in configuration space. I think that for GRW theory to make sense, it also needs a primitive ontology, something that is stuff in three-dimensional space. And here are two proposals for that: the flash ontology and the matter density ontology. Let me explain. The flash ontology assumes that instead of particle world lines in space-time, there are world points. Okay, so a macroscopic object consists of a galaxy of these flashes, a huge number of these flashes. So what you see in this picture is a space-time diagram. Space in this diagram is two-dimensional and time is upwards. And well, what you can roughly see is you see a large number, thousands of little points, little dots. They're space-time points. The matter is just at these space-time points. And of course, in total altogether, they form this kind of shape, this kind of helix shape. So that's like a binary star. You have kind of, in three-dimensional space, you have kind of two balls circling around each other. So that's what you can read off from these flashes. So here are kind of an overview, different possible ontologies that people have considered. Suppose a theory talks about particles in the literal sense having world lines in space-time. So in space-time, you have curves, a snapshot at a particular time in space. Here, only two dimensions shown. You have points. Okay, a macroscopic object, such as a table, could be recognizable in just a large number of points. Then we say that T has a particle ontology. That's the case in classical mechanics or Bohmian mechanics. A different possibility, a theory T prime, says that matter is continuously distributed in four-dimensional space-time with a particular density function m of t and x. So that's what it might look like in space-time, or a snapshot at a particular time. That is a cross-section, a horizontal cross-section through this picture, 2 dimensions shown, could have some matter density, um, and you could still recognize some objects such as tables in this matter density function. Okay, now for GRW, 2 possibilities have been proposed for this primitive ontology. One is the flash ontology that was proposed by Bell in 1987. You put a flash at every collapse center. A flash is a space-time point at the time of a collapse, at the location of the center of the collapse. There you put a point. So now you know for a macroscopic object, you have a collapse every 10 to the minus 7 seconds. Okay, so in a macroscopic object, you have 10 to the 7 flashes per second. So that gives kind of this macroscopic object a kind of definite shape on the macroscopic level. Okay, now it consists of these 10 to the 7 space-time points. Competing proposal, the matter density ontology, says the following. You take the GRW wave function that has collapsed already. You take the psi squared distribution. Psi squared, since the wave function is a function on 3 n-dimensional configuration space, psi squared is a density function on 3 n-dimensional configuration space. Now you project it to 3 dimensions. You take the 3-dimensional marginal of this 3 n-dimensional density. That is, you integrate over all your variables except for 3 ones. Here you could express that in terms of a 3-dimensional delta functions, which gives you which means that for the integration variable qk, which is somewhere in here, you plug in the value of q that you have on the other side. And maybe since now you made an arbitrary choice which k to choose, maybe you average over all the possible k's, and maybe a natural choice of the weights of this average would be to use the masses for that. But basically that's not kind of determined mathematically. It's just one particular choice. It would be, this equation would be a law of the theory. The law says, whenever the wave function is psi, then the distribution of matter in 3-dimensional space is continuous with this particular density function. Okay, so it could also be written as an expression that would kind of look like the quantum average of the mass density operators. Okay, so these two, now GRWF and GRWM are actually 2 different theories, but actually they're empirically equivalent. So whenever in GRWF a needle points to a particular value, then also in GRWM the needle points to the same value. Okay, although it's a different theory. One says, oh, matter is concentrated in just finitely many points in space-time. The other says, oh, matter is continuously distributed over space-time. So it's the flashes or the matter density function m that replaces the particle trajectories of Bohmian mechanics. Now, this concept of primitive ontology is not so easy to understand. Okay, it's so let me try to explain this a bit more. Why would anybody think that after having these collapses, that it's not enough just to have a wave function? So I will describe some reasons why people think that. Here's one. There's a logical gap between saying psi is the wave function of a live cat and saying there is a live cat. So if you have a wave function of a live cat, so it's a wave function on configuration space, and it's kind of concentrated in a certain region where configurations look like live cats. But that doesn't really mean there's a live cat in 3 dimensions. Usually, when you say there's a live cat, you mean that in 3 dimensions, there's a physical thing that is a live cat. For example, in Bohmian mechanics, the statement 2 follows from statement 1 by virtue of a law of the theory, which says that the actual configuration is psi-square distributed. If the actual configuration is psi-square distributed and psi is concentrated on the configurations of live cats, then the actual configuration will be the configuration of a live cat, at least with probability very close to 1. So we have used a law of the theory in order to go from the wave function to an actual live cat. So that could give you the impression that you need to use some law of the theory to actually obtain things like cats. For example, you could imagine Bohmian particles guided by a GRW wave function. So here's a paper where that is discussed. The particles then actually behave in a catastrophic way. Although the wave function looks reasonable, you see these GRW wave functions, they look better than ordinary wave functions because you don't have the macroscopic superpositions anymore. Nevertheless, the Bohmian particles then do horrible things because sometimes the Bohmian particles end up to be in the wave packet that gets deleted by the collapse, or it doesn't become exactly 0, it becomes very close to 0, and then once it is very close to 0, then the particle trajectories become very strange and unreasonable. So that suggests that if you haven't specified the primitive ontology, you don't know what cats or pointers actually do. From just the wave function alone, you don't know. Here's some further reasons. A second slide on the question why we need a primitive ontology. Without a primitive ontology, some paradoxes arise. Here's an example. The paradox is the following. One might think that GRW theory actually fails to solve the measurement problem for the following reason. Suppose you have a superposition like this, a superposition of macroscopically different states. Think of Schrödinger's cat or needle here, needle there. Okay, if the two coefficients are of same magnitude, then we've already discussed there's a problem. You have the measurement problem. Okay, there's no fact about whether Schrödinger's cat is actually dead or alive. Now go away from equal magnitude. Let's say one is a bit larger than the other. Okay, if it's just a bit larger than the other, you would say there's still a problem, even if one is 60%, the other is 40%. That doesn't mean that the 40% thing is not there. It doesn't mean that the cat actually is alive. Okay, now suppose C2 is close to 1 and C1 is close to 0. Has the problem gone away? How small would C1 have to be for the problem to disappear? This is a kind of slippery slope argument. Slippery slope means you can always go a little farther, and there's for making a little step, there's never a reason for changing your opinion drastically. So if you think there was a problem with root 1/2, then you should also think there's still a problem with root of 0.4, and you should still think there's a problem with root of 1/10, and so on. Here's the answer to that paradox. The reasoning misses the primitive ontology. The paradox actually is a problem if you insisted that GRW had just the wave function, but if in addition to the wave function, you also have a primitive ontology, flashes or matter density, then the problem disappears. That's because then you actually have some object in 3 dimensions. And then you can ask whether this object in 3 dimensions looks and behaves like a live cat. And if it does, then you say there is a live cat. Now you could still see some problem. Okay, here's my next slide. Another paradox. Suppose now that after GW collapse, one coefficient is near 1 and the other coefficient is near 0. But it's not exactly 1 and exactly 0. Now, if we made a measurement of the macrostate, there's a positive probability, C2 absolute squared, for finding the psi2 contribution. So how can we say that a cat with this kind of superposition is really dead? If there's a non-zero probability of finding it alive if only we look. Here's the answer. Again, that would be a problem if you had no primitive ontology, but the problem disappears once you have the primitive ontology. Here's how. When you say, for example, in GWM, the cat is dead, you mean that the thing in 3 dimensions, the M function, it looks and behaves like a dead cat. The measurement might affect the wave function, might change psi from this superposition to something near the alive state. And then as soon as that happens, which has tiny probability, the cat is actually alive in GWM. So the upshot is GWM allows for resurrections meaning somebody dead becoming alive, but only with tiny probability. Okay, the probability is so close to 0 that it's not practically relevant. It's not something that that would give rise to a worry about GW theory. Here's another advantage of having a primitive ontology. So this concerns a Bell experiment. In lecture 4, I will discuss Bell experiments in detail, but maybe many of you are familiar with Bell experiments. You have a pair of entangled particles, let's say in the singlet spin state, and you have one particle in space-time region A and one particle in space-time region B, and you do a spin measurement on each particle. Okay, now let's say that now we consider the reduced density matrix of particle A on this side, but we could consider different surfaces for that. So here are 2 space-like hypersurfaces, sigma 1 and sigma 2. One is before Bob's measurement and the other is after Bob's measurement. And now before Bob's measurement, the reduced density matrix, the partial trace, you take the partial trace over B, of Alice's particle will be a multiple of the identity, a mixed state. But on the other surface, after it has already collapsed on Bob's side, it will be a pure state, either up or down on Alice's side. Okay, so that means that the physical state of affairs on Alice's side, on this piece of surface, depends on how you extend the surface to Bob's side, whether you take sigma 1 or sigma 2. And that sounds unreasonable. You wouldn't say that the state of affairs on Alice's side depends on whether in some distant region, let's say in some other galaxy, you use this or that space-like surface. But the problem disappears if you have a primitive ontology, because then you could say, okay, the facts about what is there locally, the M function or the flashes, they're unaffected by whether I take this or that surface. Only the wave function is affected by which surface I take, and that's okay. Okay. Good, so that's some explanation of the primitive ontology. Now I want to turn to some other aspect. So now we have, now I'm basically done with my discussion of GW theory. Okay, so We've seen Bohmian mechanics, we've seen GW theory, and now I'd like to talk about limitations to knowledge, one of the surprising features of, of both theories, but actually, I would say a surprising feature of quantum mechanics in general. What does that mean, limitation to knowledge? It means that some things are real, but you can't measure them. Here's an example that applies to any version of quantum mechanics. You can't measure a wave function. Here's a specific version of that. Suppose, consider again two experimenters, Alice and Bob. Alice chooses a direction A in space. Okay, any direction is good. She chooses one. Now she prepares a spin 1/2 particle with the spinner with spin state, spin up in direction A. She hands that particle over to Bob, and the challenge for Bob is to determine the wave function or determine this direction A. So this is more or less the same problem. Now, according to the rules of quantum mechanics, so Alice knows what A is, but she doesn't tell Bob. Okay, so Bob just gets the particle, and now he can do experiments on the particle, measurements to find out information about what Alice has done. Okay, so according to the rules of quantum mechanics, Bob can do no better than perform a Stern-Gerlach experiment in some direction. So he chooses a direction B, and he does this experiment, a spin measurement in this direction. He obtains one bit of information. The outcome of his experiment will be either up or down, +1 or -1. Now, obviously, on the basis of one bit of information, you cannot determine what A is. He can conclude whether A is more likely to lie in the hemisphere closer to B or closer to -B. So if B was this direction, then hemisphere closer to B is this one, the hemisphere closer to -B is this one. So he can say something about whether it's more likely to be in this hemisphere or in that hemisphere. Okay, but that's, of course, very far from determining what A is. Now, if the game is repeated and Alice always prepares the same psi, then Bob can do better. Then Bob can determine psi to any desired accuracy, but not in a single run. And we're playing this game only once. Or we could say in every one, Alice makes a new choice. Now, nature knows in every single run what psi is, or at least that an experiment in direction A must yield up with certainty. Okay, so nature has some information about what A is. The upshot of this consideration is that certain variables have well-defined values in the world, known to nature, although we cannot measure them, even with all future technological advances. It's not a question of how good our technology is or when it will be better. According to quantum mechanics, Bob will never be able to determine psi or determine A. There's just it's just an in principle limitation. Now, when you think about it, this sounds shocking. Why is it shocking? It's shocking because it would seem to conflict with certain principles of science, such as the following. I've formulated it here. It's actually, I put it in quotation marks, but I actually made it up. I didn't quote anybody here. So nobody actually said it this way. But let me give words to what the idea would be, what the most extreme version of this principle would say. It would say, a statement is unscientific or even meaningless if it cannot be tested experimentally. Likewise, an object is not real if it cannot be observed, and a variable is not well defined if it cannot be measured. But okay, now limitations to knowledge contradict that. So the wave function is a variable that is well defined in nature. Nature knows what the wave function is. Of course, let's say up to global phase factors or something like that. But you cannot measure the wave function. Bob, if Alice doesn't tell him, Bob cannot find out what it is. So limitations to knowledge are a fact of quantum mechanics. We got to get used to them. So the principle that I formulated here is actually not a principle of science. It is wrong. One could say it is an exaggerated form of positivism. Positivism is the idea, well, it's something in that direction that in science we should only talk about, only make testable claims, something like that. Okay, now maybe a certain dose of positivism is healthy, but this is exaggerated positivism, and this is something that is not true in quantum mechanics. Limitations to knowledge are unknown in classical physics, but common in quantum physics. So here's another example of a limitation to knowledge. Consider two orthonormal bases of a Hilbert space. Let's say we're talking about a two-dimensional Hilbert space, spin state of some particle. Okay. One is the A basis and the other is the B basis. Okay, here's the A basis consisting of two orthonormal vectors, and here's the B basis. Here's A, here's B. Okay, now Alice chooses either A or B and prepares an ensemble of particles of the following kind. In her basis, she prepares, let's say, half of the particles with one basis vector as the state and half of the particles with the other basis vector as the state. Say she produces 1,000 particles like that. And then these particles are handed over to Bob. And the challenge to Bob is to determine whether Alice chose A or B. Now, the relevant fact is that Bob can't find out empirically. The two ensembles are empirically indistinguishable. This is another limitation to knowledge. There is a fact in reality whether the ensemble is actually A or B. Why is that? Well, Alice, let's say Alice kept a record of every single particle of the 1,000 particles, saying which vector it was prepared in. Okay, so she can say, oh, particle 1 was prepared in this vector, particle 2 was prepared in this vector, particle 3 was prepared in this direction. And you can check, of course, afterwards. If you have Alice's notebook, you can check whether it is correct. According to the rules of quantum mechanics, you can make the prediction, okay, if you measure in this direction, you get result +1 with certainty. Okay, you can verify that Alice's notes are correct. And that means that there is a fact of whether the ensemble consists of these two quantum states or those two quantum states. But Bob can't find the difference. He gets the same probabilities for every experiment that he does. How can he prove this, that he gets the same probabilities? Well, for every projection operator P, so for example, if it made a quantum measurement of some self-adjoint operator, okay, then the probabilities would correspond by Born's rule to the projections for the eigenspaces. But then when he does the experiment on, say, 100 of these particles, then the statistics that he finds, according to the prediction of quantum mechanics, is, oh, for half of the particles, you get this probability here. For half of the particles, you get that probability. So in total, you just get 1/2 times the trace of this projection, which means now this projection, let's say these eigenspaces are one-dimensional, you get the value 1/2. Whatever, independent of whether Alice chose A or B. Okay, so all of this is not deep. This is a kind of easy exercise in the mathematics of quantum mechanics. But what it shows is that there are facts out there in reality that you cannot determine through any experiment. And this is something that we need to keep in mind when discussing questions of foundations of quantum mechanics. So the essence is that nature can keep a secret. Actually, this plays a role for schemes of quantum cryptography and similar things. And these limitations to knowledge become particularly visible in these theories that are such as Bohmian mechanics and GRW. Here's a particular example from GRW theory. In GRW theory, well, there occur these collapses. So in nature, there's a fact about how many collapses occurred. These collapses occur stochastically. So the number is only on average predetermined, but not exactly predetermined. So you could try to measure the number of collapses that actually occurred during a particular time interval. Say you have a kind of small system, kind of mesoscopic system, a not too large number of molecules, at a particular time interval, 1 second or less. Could you have something like a Geiger counter for collapses? Could you in any way measure how many collapses actually did occur? The short answer is no, you can't. There are limitations to the precision, to the accuracy with which you can determine whether a collapse has occurred. You can do probabilistic statements. You can do some measurements on the basis of which you can make probabilistic statements of how probable it was, but you cannot make that arbitrarily precise. In GRW theories, nature knows the exact number of collapses, but inhabitants of the GRW universe can find it out only with macroscopic inaccuracy, let's say plus or minus 10 to the 9 collapses per second. So in these papers here, the analysis is done in detail. That's the end of my second lecture. Thank you very much for your attention. So if there are questions, I'll be happy to answer questions.
May I ask a question?
Sure.
Is there a possibility to test Bohmian mechanics experimentally?
The predictions of Bohmian mechanics agree exactly with the predictions of the standard rules of quantum mechanics. So you cannot test between these two, rules of quantum mechanics and Bohmian mechanics. Now, you could say the following. You might think of, well, maybe could I test perhaps Bohmian mechanics against Copenhagen? Well, you could perhaps say, you see, Copenhagen, that's not a kind of, not a good comparison, because Copenhagen doesn't have a clear ontology. It's not completely clear what Copenhagen actually says. So I'm comparing apples to oranges. You could ask the question, okay, could I test Bohmian mechanics against GRW? Oh yes, that's possible. So if this island shrinks to 0, and then you could say now GRW theory has been refuted, so Bohmian mechanics is what we are left with. But it's not possible to test Bohmian mechanics against the rules of quantum mechanics. The rules of quantum mechanics are theorems in Bohmian mechanics. But you could say, well, it would be the right kind of question to ask, to test between a theory and just a set of rules for making predictions.
Okay, so that makes Bohmian mechanics more like a philosophical interpretation and nothing else than that. So there's no empirical value behind that.
I would say that's a way of putting it that is a bit misleading, because you see, the question of what's going on in a double slit experiment is kind of a physics question. It's physicists who would like to understand how the double slit experiment works. It's physicists who would like to know what happens inside an atom. And to say, oh, this is a philosophical question is, I would say, well, doesn't quite do justice. Let me give you an example. It's an example that's actually due to Richard Feynman. Consider an ancient astronomer. The astronomer is concerned with the motion of the planets. Okay, but to him, the planets are just bright spots in the sky. Okay, he doesn't know that planets are balls of rocks moving around. Well, Feynman had this example with Mayan astronomers. Okay, in Central America. Okay, so maybe for them, they were just concerned. Maybe they didn't talk about the nature of the planets. They didn't ask about the motion in 3 dimensions. Maybe the Greek astronomers had some ideas about how planets move in 3 dimensions. But the Mayan astronomers just were concerned with predicting eclipses and predicting the motion of these spots in the sky. And you see, or Feynman argues, the Mayan astronomers, if somebody had come to them, a student, and said, oh, I have this idea that these planets, these spots in the sky that move around, that they're actually giant balls of gas or rock, and they're moving around in a certain way, and I'm thinking about which way they could move, then the astronomer might say, oh, yeah, look, the only thing that you could test is how they actually move, where the point is in the sky. And look, we have very accurate methods of computing how they will move in the sky. So what does your hypothesis add to that? Now, what is different in this example than in the case of Bohmian mechanics is that in this example was several hundred years later, it was possible to actually travel to the planets and so gain access to very different kinds of empirical facts. Now, in the situation of quantum mechanics, there's no reason to think there will ever be any further empirical facts that would somehow make a difference between Bohmian mechanics and Copenhagen quantum mechanics, or just the predictive rules of quantum mechanics. But the point remains that when you understand Bohmian mechanics, you can think about the situation in a different way. You don't make certain mistakes that one could easily make when one just thinks of it in an operational way, like Wheeler's fallacy. You could also say that it's one of the goals of physics to understand how the world works. We want to know what planets actually are. We want to know what actually happens inside an atom. And then it might seem strange to say, once we've reached quantum mechanics, that now we don't want that anymore. So that's why I would say it's not just a philosophical question. Saying it's a philosophical question makes it sound like it's not the business of physicists. I think it's very much the business of physicists.
Okay, thank you.
Are there other questions?
Maybe I would like to extend a little bit the previous question.
Yes, please.
I agree that the kind of the way we perceive our formulas is super important, actually. So then I would like to extend the question the following way. Is it possible in principle, let's say, predict or have different or slightly different predictions for certain phenomena from different interpretations or somehow different interpretations, let's say, of the quantum mechanics. In a kind of, in a sense, that whether it's possible to test our ideas, in the sense that whether some of these ideas are actually about the nature or it's just our fantasy.
Okay, I think the word fantasy gives a bit the wrong impression here. I would say hypotheses instead. And I think, or theories. And I think it's important for physicists to come up with hypotheses or theories. Now, the situation is, you see, in the Copenhagen interpretation, you run into theoretical problems, such as the measurement problem. So it's not an empirical question, not that the predictions are wrong. It's a kind of a question of internal consistency. So that is a problem that bothers many people. But that is a problem that can be solved. So Bohm has a solution to that, GRW has a solution to that. So for theoretical reasons, you might be inclined to say, I want to consider theories such as Bohm's or GRW's. Now, among all of these theories, some can be distinguished from each other empirically, such as GRW from Bohm. The predictions are different. In some cases, some of these theories make exactly the same predictions. So for example, in the literature, people have discussed different versions of Bohmian mechanics that make exactly the same predictions for every conceivable experiment, but are different theories, make different statements about how the world works and what is there, about the ontology or the equation of motion. Now, in these situations, it's not possible to decide the question empirically, but that doesn't mean that each of these theories is somehow equally likely or equally convincing. What happens in most of these examples is that some proposals are much more physically convincing than other proposals. For example, Edward Nelson in the 1960s had proposed a theory that is often called stochastic mechanics. It has particle trajectories like Bohmian mechanics, but these particle trajectories are not solutions of a differential equation. They are stochastic curves like Brownian motion. Okay, so they're a variant of Brownian motion that is psi-square distributed at every time t. Now, when you think about the question of whether it seems convincing that this is how nature works, then it seems to, well, to most people who have thought about the question, that Bohmian mechanics is far simpler than stochastic mechanics, and therefore seems more convincing than stochastic mechanics. So these two theories, there's an example of two theories making different statements, but the same empirical predictions. And then for theoretical reasons, one of the theories seems more convincing as a theory of nature than the other. Okay, so there could be reasons for preferring one theory over a different one, even if the two theories are empirically equivalent.
So then can I ask her in a following way that are some of the interpretations technically easier to use or not really?
I think when it comes to computing the predictions, they all amount to the same rules. You have the collapse rule, Born's rule. Okay, you will use in the end the same self-adjoint operators, the same eigenvalues, the same eigenspaces, the same projections. Well, I guess maybe there are two advantages. One are if you have a clear picture of what actually happens in reality, that gives you a clear justification for why these rules are correct. So this is a kind of theoretical advantage. Another thing, maybe there's also a practical advantage, that if you have a picture such as Bohmian mechanics, it could give you new ideas that you don't have without this picture, such as you would use different approximations that without the Bohmian trajectories you wouldn't think of. So Bohmian mechanics has led Bell to the discovery of Bell's theorem. It has led to certain approximation methods for semi-classical trajectories, or approximation methods for the time evolution of the wave function, certain numerical algorithms for efficiently solving the Schrödinger equation are based on Bohmian trajectories. Certain approximations for how to compute time of arrival statistics are based on Bohmian trajectories. Okay, so there are sometimes there are practical aspects where the Bohmian picture gives you certain ideas that you wouldn't have otherwise.
Essentially, it means something like our introduction of or introduction of Feynman diagram. So before Feynman, also people calculated these amplitudes, but in more complicated ways. It was hard to compute it because it was hard to imagine. In this sense, maybe it's also very useful to have some ideas like Bohmian mechanics.
Yes, so it seems to me comparable. So the practical advantages for doing calculations of Bohmian mechanics might be similar to the practical advantages of Feynman diagrams. But let me say, I mean, the reason I'm talking about Bohmian mechanics here is not the practical advantages, it's the theoretical advantages. Okay, so that is what motivates me. That's why I think this is an important question.
Thank you.
So there's somebody else raised a hand, Robert Gartman. You want to ask a question?
Oh, yes.
Okay.
Sorry.
Sorry. Okay.
You were mentioning these random jumps in energy in the GRW theory, depending on the width of the Gaussian. And I was wondering, how is this consistent with energy conservation?
So in GRW theory, energy is not conserved, but it's only a small deviation from energy conservation, so small that it becomes hard to detect experimentally. But it is a consequence of GRW theory that energy is not strictly conserved. It's over time, it's going up and up. So the universe is spontaneously warming if GRW theory is correct.
Okay, thanks.
Okay, let's see. Now, Mr. Gartman writes, my microphone does not seem to work anymore. Okay, you want to ask a question via chat? How does the ever so slight energy increase for isolated systems manifest? Electromagnetic, kinetic, entropy, no specific form. It occurs in two ways. One is that each of these collapses concerns one particular particle, and with a small probability, a large amount of energy is kind of injected into that particle. So as a consequence, if GRW theory is true, then sometimes when a collapse occurs, one of these particles, the particle hit by a collapse, suddenly has very large energy. And that would lead to consequences such as, I don't know, spontaneous emission of gamma rays. So one way of testing GRW theory is to look whether you have these spontaneous gamma rays. Okay, people have have done such experiments also for other reasons, or used the data that have come from other experiments that also yield information about about emission of gamma rays. And the consequence was, that puts some constraints on the parameters of GRW theory. So at this point, these experiments have not confirmed GRW theory. So the amount of gamma rays seen was consistent with standard quantum mechanics or with Bohmian mechanics. They have not seen these excess gamma rays. Okay, now Mr. Gartman writes, so maybe testable with experiments similar to Super Kamiokande as well. Okay, I don't know. I don't know that experiment.
It looks for proton decay.
Okay.
So it looks at, it's just a big mass of water, which also acts as a neutrino detector.
Okay.
And then they have a bunch of PMTs.
Okay, so maybe in these experiments, you should see such kind of bursts caused by spontaneous collapses as well, if GRW theory is correct. And if you don't see them, or if you have kind of upper bounds on how many of them you see, then that should put bounds on the parameters of GRW theory. So that should move this, the boundary of the empirically refuted region further towards the southeast. The other way in which the energy increase due to GRW collapses should manifest itself is to an overall increase of temperature. So if this particle that has a lot of energy hits many other particles, then the energy quickly gets distributed over many particles, but still you should see an overall increase in temperature, a spontaneous increase in temperature. So for example, people have looked at whether the intergalactic medium, kind of a huge, very dilute gas, whether it spontaneously warms up. Now there are kind of different factors that are relevant to the temperature balance of this intergalactic medium. The medium absorbs some photons, and then there's some cooling due to expansion, cosmic expansion, and maybe some other factors. The upshot seems to be that no significant excess warming of this medium has been observed. So that is consistent with GRW theory being wrong. And it puts bounds on the parameters of GRW theory. So it contributes to to where the boundary of the empirically refuted region lies in the parameter plane.
Are you aware of any efforts to bound GRW using neutrino oscillations? Because I work in neutrino oscillations, and I've thought maybe it could be relevant.
Yes, I think that Philip Pearl has a publication on how neutrino oscillations, how they put bounds on the possibilities of collapse theories. Now, I don't know details about that, but I think the answer is yes, there are such considerations.
Do you know when that was done? What year?
Maybe 10 years ago. So the name Pearl is spelled P-E-A-R-L-E.
P-E-A-R-L-E.
Okay, now somehow I wrote it to the, I have to, how do I send a message to everyone? Okay, everyone. Okay, let me write it in the chat. Pearl. So that's the name of the researcher who did the comparison. Okay, other questions?
But I do have a question, probably a silly question, but the Bohmian mechanics happen in Euclidean space. I was wondering if it's possible to extend it to four-dimensional space, and what does that imply?
Yes. Actually, in lecture 4, I will talk about how to do Bohmian mechanics in relativistic space-time. So yes, so maybe I don't say a lot now, but ask you for some more patience and wait for lecture 4.
Super.
Okay.
Another question from my side. In the GRW, we have these stochastic collapse processes that happen at random. On the other hand, in the Bohmian mechanics, there doesn't seem to be an intrinsic part of randomness that happens during the entire process of these trajectories, just an initial random distribution that gets propagated quasi-deterministically. Is this am I making a mistake understanding there, or does that mean that from the Bohemian point of view, we have one initial starting configuration of the universe, and then could, in principle, if all things are known to, in this case, nature, know in advance what will happen?
That is correct. Bohmian mechanics is a deterministic theory. So the configuration at any time t is some function of the initial configuration and the initial wave function. Now, for inhabitants of the Bohmian universe, that is not useful. They cannot use this fact in order to predict the future because for them it's impossible to have full knowledge about the configuration of systems. So whenever they know the wave function of a system, they cannot know the particle positions, the configuration, more precisely than the chi-square distribution allows. But in principle, it means, yes, according to Bohmian mechanics, the evolution is deterministic. However, I should say that as soon as you try to include particle creation and annihilation, okay, then you would have to extend Bohmian mechanics. And okay, there has been some debate in the literature about how to do that. But maybe the most natural way of doing such an extension is then actually stochastic. So if you include particle creation, as presumably you should for a more realistic version. So what I presented here was just for non-relativistic quantum mechanics with a conserved number of particles. But if you want to go to more realistic situations, then the theory becomes stochastic as well. Actually, the processes of particle emission, like photon emission by an electron, becomes stochastic. The time at which the emission occurs and the direction in space in which the boson gets emitted, they would be stochastic. So in this sense, also in these versions of Bohmian mechanics, the nature would make some random decisions in the middle of history. Maybe let me add one more remark. Many researchers working on this subject feel that, well, deterministic or stochastic, it's not such a big difference. Stochastic would be equally acceptable to them equally acceptable as deterministic. For example, Bohm also considered some models that were stochastic. John Bell proposed a stochastic model of particle creation. So often, let's say the bigger difference is between theories like Bohm and GRW on one side and Copenhagen on the other side. And the difference between stochastic or deterministic theories, well, it is a difference, of course, but many researchers in the field would not be prejudiced about it. They wouldn't say, I cannot accept stochastic theories. They would say, okay, so if the stochastic theory is more convincing, then maybe nature is stochastic.
Thank you for the answer.
Any further questions?
Yeah, I have one question.
Okay.
About this Bohmian quantum mechanics. Not sure if I understood this concept of real trajectories. So if you would go from a double slit experiment, for instance, to a Arnold-Bohm experiment, where you modify the interference pattern by adding a phase to the electrons, which pass an area where you have a non-zero vector field but a zero electromagnetic field. So in the Bohmian picture, would it mean that you modify the trajectory without the presence of a electromagnetic field, or?
Yes, exactly. What would happen in the Bohmian picture is that as you change this the current in the in the coil, you change the vector potential, you change the evolution of the wave function, and the Bohmian trajectories, they depend on the wave function. So with the different wave function, then the Bohmian trajectory will curve in a different way and will end up in a different spot on the screen.
Oh, okay.